So today we will discuss about Huffman codes, which are one of the prefix codes that I promised we will talk about in the lectures. And we'll do some examples, look at some real life applications. So let's get started. So again, you go to the website. Again, remember, don't go to the last year's website, go to this year's website, right? Fall 2023, 2024. Once you are here, click on lectures. And then here you see we have also released a tutorial. So click on the tutorial. Right. So gives a broad overview of SCL, how to install, how to use it, right? And then there are like sub pages. So there is a SCL basics section that shows you the structure of the library, what you can find in the structure, some of the interfaces, right? So we tried to have some interfaces that are common across a bunch of compressors so that life becomes easy. Like we will see actually for Huffman code today how some of that makes your implementations very easy. You just need to focus on the logic, not on the all the stuff around it. So data blocks, data encoder, decoder, probability distribution related stuff like getting empirical distributions, computing entropy, that sort of thing. Some standard compressors that we implement, some others you will implement as part of your project or as your homework. Some utility stuff like working with bits versus bytes and working with trees and so on. And then there is a sort of an exercise. The exercise is actually a question from last year's homework 0, which we this year decided to provide as an exercise. So you can just go through it with the solution and just see how you can use the library. So this has questions and answers. And there is a Colab notebook linked here, which you can look at, which just shows the working example and the test passing here. You can see. Yep. Okay. Any questions so far on the announcements on SCL, on the homework?
I'll just add one part. So the Colab notebook is also for you guys to just see how you can use SCL with Colab, which might be useful for some of your project stuff even going ahead. Just trying out things on Google Colab. So it's just one cell that you need to run, so you can have a look at that.
Yeah, so Pulkit just announced that the Google Colab notebook, it has the steps to install SCL into a Colab notebook, which will be useful for you in your projects. It was useful for me for today's lecture actually, as I was trying to do a demo. So yeah, take a look. Okay, let's move on. So let's recap very quickly. And in the recap, I won't dwell on things that you don't need as much going forward, more on the things that we'll focus on. So more on the results, less on the proofs. We learned about Crafts inequality, right? Crafts inequality was an if and only if condition for prefix code. So you are a prefix code if and only if your lengths, no, not really if and only if. If you're a prefix code, then your lengths satisfy a certain inequality. And if the lengths satisfy a certain inequality, then you can create a prefix code out of it, right? So that was Crafts inequality. We won't need it really. You have a question in homework about proving it for uniquely decodable codes. So good luck with that one. Okay. Entropy. We defined entropy. Entropy is sort of the fundamental quantity for lossless compression. It's the lower bound on the best compression possible. And it's defined as this formula. And you had some quiz questions to help you get more familiar with it. We talked about joint entropy for IID variables, where if you have n IID variables x1 through xn, then their joint entropy, so you can do it in 2 steps. So the first step is that the joint entropy is the sum of the individual entropies. This step uses independence of the random variables. And the second step uses the fact that they are identically distributed so that the entropy of the sum is the n times the entropy of a single one. All of them have the same entropy. And then we defined KL divergence. I'm very quickly recapping. If you have questions, please let me know. So KL divergence was this other quantity. This had 2 variables P and Q, so 2 probability distributions. It's sort of a distance measure. So it is greater than or equal to 0 with equality if and only if P is equal to Q. And you again had some questions in your homework about this. Then the other big thing we did last lecture was the main result, the real main theorem of lossless compression, that for any prefix code, the homework you will see for any uniquely decodable code, the expected code length is lower bounded by the entropy. So you cannot do better than the entropy. And the other part was that you can actually achieve entropy or get arbitrarily close to entropy if you work with blocks. Okay, any questions so far on last lecture? Okay, let's move on. Towards the very end of the last lecture, we talked about the achievability part, like how do you actually achieve this, right? So the first thing we did was we took the Shannon codes, we know their lengths, we did this calculation with the ceiling function and so on. And what we got was that the expected length for the Shannon code is sort of sandwiched between entropy of x and the entropy of x plus 1. And we saw some examples, and you saw one in quiz, which we'll see shortly, where Shannon codes didn't do as well. Like you clearly could see that Shannon codes were very, very bad. And Shannon codes are not the optimal codes, and we'll look at the optimal code today, the Huffman codes. The other thing we saw towards the very end was that if you code in blocks of n, then the average code length per symbol you can achieve using this formula we saw just now, right? This one, that the entropy of xn is equal to n times the entropy of x. You can get basically within 1 by n of entropy. So working with blocks is really the way you get arbitrarily close to entropy. And it's very important working with blocks. You will see, like as we go through the lectures, that there was a progression in compressors. The very early days compressors like gzip, they used to do Huffman coding, which doesn't work with blocks really. And they didn't get like very good results. And all of the compressors today, the modern compressors, all of them work with blocks. But they don't work in blocks like the way you worked in blocks when you did your homework question. There are better ways to work with blocks, which we'll learn about next week. So topic for next week, we'll come back to this. Okay, let's keep going. Let's look at the quiz, which will also help motivate some of today's questions. So you have a Bernoulli P random variable, right? Bernoulli is like one of the simplest distributions. You have 0 and 1, and probability of 1 is P, probability of 0 is 1 minus P. So the first question was, what is the entropy of X as a function of P? Anybody? Anyone wants to? I assume all of you did it. Okay, let me write it down. So it is P log, it's just the formula, nothing very clever. So this function, this is in literature, it's sometimes written as H2P, sometimes it's written as HBP. So binary entropy function, that's what it's often called. And you can like even plot it as a function of P. Let's call it HBP. So what is the value at 0? What is the entropy of Bernoulli 0? Yeah, I see some people saying 0, which is correct, right? We learned last lecture that the entropy, if you have a random variable which is deterministic, its entropy is 0, right? There is no randomness. Bernoulli 0 means that it's always equal to 0. It's never 1. So the entropy is 0 at 0. How about the entropy at 1? When P equal to 1. So P equal to 1 means that it's always equal to 1, never equal to 0. Yeah, a few people said also 0, right? You can put it in the formula. Remember that P log 1 by P is defined as 0 when P is equal to 0. So it's also 0 at 1. How about at half? Yeah, for half I see here 1, right? So half means that it's like equally likely to be 0 or 1. So then the information content is 1 bit, right? 1 bit, it's either 0 or 1 with equal probability. So it's 1 at half, and you can prove in your information theory course that it's a concave function. So it looks something like this. It's symmetric around half, as you can see in the expression as well, right? And yeah, not much to say other than you will see this function a few times. If you do information theory, you will see it a bit more. It's very flattish around half, you will see. So whether you have a Bernoulli half variable or you have a Bernoulli 0.4 or Bernoulli 0.6, you will see it hardly like makes a difference in how compressible your file becomes. So there are some like practical observations around entropy's concavity that you might encounter. Okay, yeah, please stop me if any questions. Then we asked you to do the KL divergence between Bernoulli P and Bernoulli Q. I will just write down the expression. Please talk to me later if you had any trouble. Again, just like following the formula. Okay. Is this correct? Okay, I see some notes. Good. Okay. And then we asked you to compute this Bernoulli 0.3, 0.7. I assume you computed it. Just plug it in the formula. So you will see the quiz questions are mostly meant to like make sure you're following what's happening in class, right? They're not most of the times not supposed to like require very advanced thinking, right? Okay, this one. So what we asked for is what is the maximum KL divergence between Bernoulli P and Bernoulli Q if you are allowed to vary P and Q sort of in their entire range of 0 to 1. What was the answer that people got? Yeah, I hear infinity. Yes. So the KL divergence can be unbounded. It can be infinity. And in this expression on the last page, if you set Q to 0 and P to 1, then you get 1 log infinity. Yeah. Yeah, so this is infinity. Not much to say. It's like it goes from 0, right? Minimum is 0. When P equal to Q, it's 0. And when one of them is 0, then it becomes infinity. Yeah, you will see that between probability distributions, there are like two very common ways to measure the distance. One of them is KL divergence. The other one is something called total variation distance or L1 distance. So depending on like what application you're working with, you either prefer one or the other. The total variation thing is symmetric. It's never infinite. It's bounded. It's much nicer like in terms of its properties. But this one often works better in many of the machine learning applications. And this one is no. It is not symmetric. You can try out an example. Like even if you take like P equal to 0.3, Q equal to 0.7, you will see that it will be symmetric. But if you take this sort of thing, then it won't be symmetric. Okay, any questions on question 1 in the quiz? Okay, let's move on. Okay, this one will be more interesting for this lecture. So you have a Bernoulli 0.001, right? So it's very high probability it's a 0 and very low probability that it's a 1. We asked you to make a Shannon code for this thing, right? So you can do this calculation, right? You have probability of x and you can calculate the length, which is log 1 over probability of x, the ceiling function, and you get 1 for 0 and 10 for 1. So you can now assign the code words. Maybe you call it 1 0 and you call it 1 0 0 0 0 0 0 0 0. Right. And then you can calculate the expected code length, which is just 0.999 multiplied by 1 plus 0.001 multiplied by 10. Okay. I hope all of you got this. This is just, we have been doing this for a few lectures. Then we asked you to compute the entropy. Again, the entropy we already did in question 1. You know how to compute the entropy. And then we asked you to compute expectation of the length divided by entropy. And I got around 88. I saw some students like, I think we asked Pulkit in the question, this one, the second one, to give your answer like to 2 decimal places, right? And then if you take both the expected length and the entropy to 2 decimal and then you divide them, you don't get 88, you get 100 or something like that. So we can, I guess, make a regret request and we will look at it on an individual basis. Okay, so the takeaway really is that like for this very skewed distribution, Shannon codes are not doing particularly well, right? Like you should be spending 0.01 bits per symbol. You should be spending very few bits per symbol, but you are spending more than 1 bit per symbol. It's like a huge overhead. Not great. Okay, so any suggestions? What is the first thing we can do to improve this code?
We can cut down the code for 1, just add 1.
Yeah. So the first suggestion is that like this clearly seems suboptimal, right? Like why do we have this huge thing? So Shannon codes are good. They helped us prove something, but they are not optimal, as we have been seeing for a while now. So you can cut this down. What will be the expected length after you cut this down? 1. The expected length will be 1 because both of the things are 1, right? So it doesn't really solve our problem, right? Our entropy is 0.011 and we are still using 1 bit per symbol. So, okay. So this is the thing I just asked. This is the optimal code. This is the optimal code. You can't do better than this, right? If you have 2 symbols, you have to spend at least 1 bit per symbol. So the optimal code here is not particularly good, right? It's 1 bit per symbol, much bigger than the 0.011, the entropy. Okay. So the other thing we have been seeing for a few lectures is to do block coding. So let's like write it down. What does block coding really mean? So you create this joint symbol. Take x1 and x2, like 2 symbols at a time. So you have 4 possibilities, 0, 0, 0, 1, 1, 0, 1, 1. Then you compute the probability of these pairs. How do you compute the probability of a pair from the probability of the individual, like from the original distribution? How do you get like P01 in terms of P0 and P1? I'm hearing product. Can anybody explain why product is the correct way to do it? Can I always assume that product of 2 things is the joint thing? Well, what's the assumption, the underlying assumption here? Yeah. So the answer is they are independent, right? So this thing, so Px1 x2 is equal to Px1 times Px2 due to independence, right? So we'll assume independence for the next couple weeks and then we'll move on. Independence. Okay, so I did that calculation at home, got these numbers, right? I made the code. This is not a Shannon code. This is actually the optimal code for this distribution, and we'll learn how to make this later on. But you can see it makes sense, right? Like you give short code words to the high probability stuff, and you give longer code words to the low probability stuff. Hopefully intuitive. And then you can compute the expected length. And when you compute it, always remember to divide it at the end by 2, because now you're doing 2 symbols at a time, right? You're doing a block of 2 symbols. So I did this calculation again. And now you see it's actually closer to the entropy, right? It's 0.5 instead of 1 we had before. Still very far away, right? 0.5 is still like roughly 50 times worse than the entropy. Long ways to go. And really, you can keep increasing the block size, but it gets unwieldy very soon. The real solution is to use streaming codes, which we'll learn about next week. But for now, let's try to understand how did we even get this optimal code, right? It's not trivial. I give you any random distribution. We saw Shannon codes often do very badly. How do I get the optimal code? And that's sort of the topic for this lecture. Right. So we'll start with some conditions for optimal prefix codes. Then we'll look at the actual code. Then we'll talk about Huffman coding in practice. And you will hear some interesting things about which you might have heard in your algorithms class. So hopefully this is fun. Okay, any questions so far before we get started? Okay, let's get started. So, optimal prefix codes. So when we talk about optimal things, first thing to define is like what do we mean, right? What does it mean to be optimal? So in our case, optimal means we want to find the minimum lengths such that you want to minimize, like you want to find the length such that this sum, the expected code length, is minimized, subject to the prefix free condition or equivalently satisfying Kraft's inequality, which we saw are equivalent. So this is the definition of optimal prefix codes, right? And those of you who have done convex optimization or just generally optimization, you might want to go that way, right? And actually, if you do that, you will actually start getting some of the thumb rules that we have been looking at, like the length should be log 1 over p. In the notes, you will see that, like if you do the Lagrange multiplier stuff for this one and you proceed, you will actually get the thumb rule that we know and love. But today we will look at a different way of doing it. So this. We will define some conditions for optimality. After which it is story time. Okay. So there are two conditions for optimality. One, this one you have already seen. Right. If the probability of a symbol is bigger than the probability of another symbol, you should give it a shorter or equal length code word. Right. And otherwise, what you can do is swap. Basically, you can swap the code words and get a better expected length. Okay. So this one we have already seen. Let's look at the other one. The two longest code words have the same length. This one we have not seen before. Can anybody let me draw a code, and then we'll see like what I mean here. Right. So basically it's this guy and this guy, right? These are the two longest code words for this small code that I've drawn. They do not have the same length, right? One of them is length 2, one of them has length 3. And that means this cannot be an optimal code. Why? Why is it? Why is that? Can anybody explain?
You can look the longest one leg up.
Okay, so the one suggestion is that it is not optimal because you can take the longest one and make it shorter. And I guess in the diagram it's clear, but in general, can you argue why that will still leave the code as prefix free?
Because the longest two, like the difference would be 1 bit. Like the last bit would allow you to create two code words of the same length.
Yeah.
So the longest thing.
Yeah. So basically the answer is that if you have one code word, like the longest two code words are not equal, So the longest code word, you can basically shorten it to the length of the second longest code word. And do the math at home in peace. Basically, you will see that it cannot violate the prefix code condition. Why? Because if the longest code was a suffix of some other code, then it like basically, let's say, okay, so let's say after shortening the longest code, it becomes a suffix of some other code. You can argue that it has to be already a suffix in the original code. So it's like, let me write it down, and then I guess you can think about it more. Why still, so basically the solution is to like cut this part. Why still prefix free? Can you say it? Yeah. If shortening violates prefix property, you can argue that original code also violates, like it's, if you shorten it and then it starts violating suddenly the prefix quality, you can argue that the original code must have been already violating it. Otherwise, it's not possible that the shortening violates it. Think about it. It's not very crucial, but really, like these observations, you will see that Shannon code, the one we saw a few slides ago, actually we didn't, but the Shannon code often doesn't have this condition. Therefore, it is not always optimal. Any questions so far? I guess do you understand just understand the conditions, and the proofs are in the book, plus you can think about this. This is like relatively easy to reason about. Okay, story time. Okay. Huffman codes, right? So David Huffman was, I think, a PhD student. And he was taking a class on information theory. This was very early days. This was like a few years after Shannon had done his like 1948 paper. And Robert Fano, another very famous information theorist, was the person teaching that information theory class. So he gave students an option, like either you do a final exam or you do a project. And true story, it's not like a tale, it's a true story. So Huffman thought, why do the exam? I will do the project. It will be more fun and like easier, he thought. And the question was basically problem, right? Like find the optimal prefix code. And Huffman worked very hard. At some point he thought it's not possible, but then he cracked it. He solved the problem. And then like the professor Fano told the students that this was actually an open problem. He had just given an open problem as a project problem. Huffman at some point later said that like if he had known that it was an open problem, he probably wouldn't have even tried it. He would have just given up. So sometimes like not knowing that it's a tough problem, sometimes we underestimate our abilities. And the construction is very easy. It's a greedy construction, which we'll see in a minute. And Fano also had a greedy construction, but that was not optimal in many cases. But Huffman's greedy construction, which we will learn about, is actually optimal. So let's look at the final project of a student. So what I'm going to do is I will write down the construction for your future reference. Then we'll do one example which I will do, and then we'll do another example which you will help me with, and then we'll look at some real life examples. So first step is to create a list of nodes which is equal to, you have each symbol and its probability. So you make a list like this, okay? Then while more than one node left, we'll post these slides as you might have observed, so no need to write if you don't want to. You pick two nodes with least probability, merge the two nodes. And what does merge mean? And we'll look at an example. Create new node. Actually, how many of you have seen a Huffman code in the past? May I ask, where have you seen it?
In 106B, our final project, one of the final homeworks is like to do Huffman codes.
I see. How about you?
Where I saw
Huffman code.
in my undergrad course at Berkeley.
Right. Yeah. So we'll see that Huffman code is one of the classic examples of greedy algorithms, which you study in many computer science classes. So yeah, for those who have not seen, this is a good, I think, introduction. Okay. So we create a new node with the two nodes as children. Probability equal to sum of probability of children. And you keep on doing this sort of, it's just like a loop. And the last remaining node is the root. And one sort of asterisk, you break ties arbitrarily. Okay, so basically you start with a list, you keep merging the two lowest probability nodes, and you end up with a tree where all of your initial symbols are at the leaf of the tree. But let's do some examples. I think that's the most useful thing to do. Huffman. So the first step here is you take the two lowest probability nodes, right? So right now there are 4 nodes. The initial nodes are just the symbols. You take the two lowest ones, you merge them. What does merging mean? You basically take these two nodes, you merge them, and that creates a new node. Call it like N1, let's say. And the new node has the old two nodes as children. The probability, sum of the probabilities of the two nodes. So 0.2 in this case, okay. Now you have 3 nodes left in the tree. You have A, B and N1, right? You again take the two lowest nodes. So now the two lowest nodes are B, which is 0.25, and N1, which is 0.2. You merge those two nodes. So you merge them like this. You get another node called N2, which has probability, which is the sum of 0.25 and 0.2, which is 0.45, okay. Now you are just left with two nodes. So they are the two you will merge. You take A and N2, you merge them, you get the root node, let's call it N3, which has probability 1. And that's it basically. That's the Huffman tree, right? And then you can, like, more of an afterthought, but you can do it, like you can just label these guys 1, 0, and that gives you the code. So very simple construction. Any questions? Otherwise, we'll do another example where you will help me out. Okay, looks like we are happy. Sorry. Huffman. So this one will be more interesting. Again, A, B, C, D is this time there are 5 symbols: 0.35, 0.25, 0.2, 0.12, 0.08. So initially we have 5 nodes in the tree: A, B, C, D, E. Okay. Somebody, which are the first 2 nodes we merge? And what is the probability of the merged node? Okay, so the answer is D and D. And so let's merge D and D. Okay. And what is the probability of this new node? Let's call it N1. 0.2, right? Why 0.2? 0.12 plus 0.08 is 0.2. Good. Now, what are the next 2 nodes we merge? Some people are whispering very low voice, please. Am I hearing C and N1? Okay, let's merge C and N1. Let's call it N2. What is the probability of N2? 0.4, because 0.2 plus 0.2 is 0.4. Okay, next one. Okay, I heard N2 and B. Anybody disagrees? Yeah. So now you have 3 nodes left, right? You have N2, which is 0.4. You have B, which is 0.25. You have A, which is 0.35. The 2 lowest ones are actually A and B at this point. So you merge A and B. Right. You get N3, which has probability 0.6, because 0.35 plus 0.25 is 0.6. And now you can just merge these 2 guys, get the last root node. You get 1.0, right? And then assign like this guy. Right. Let's actually write down the code words so that there is no confusion at all. A, B, C, D, E. Okay. Code word for A. 0, 0. Code word for B. 0, 1, right? Because we drew it in a different way, right? The root is actually on the right, so you need to go from right to left. So B is 0, 1. C. C is 1, 0, right? D. Yeah, 1, 1, 0. And E is 1, 1, 1. Right. We see it has the usual, like the properties, the optimality properties we discussed just now, right? That the 2 longest code words are D and E, and they have the same length. That's good. And you can verify that if one guy has higher probability than the other one, then it has a equal to or smaller length than the other one. So it satisfies the optimality properties. Okay, any questions about the construction? Very simple construction. Really not that much to say. It's try to implement it if you want to do coding practice for some interviews or so on, right? It's a very classic greedy algorithm. See what data structures you use. Do you use recursion or do you use iterative and so on? So why is it optimal, right? Just satisfying those 2 conditions doesn't make the code optimal. You need to prove that it is actually optimal. We will not prove it in class. So we will see the lecture notes. Actually, it's not in the lecture notes. You need to see the book. So you see Cover and Thomas chapter 5 for the proof of optimality. It's like based on an argument which is roughly that A, B, C, D. Okay. So it's like an inductive argument that optimality of this guy is equivalent to so it's like a step-by-step proof where you say that if my final code is optimal, that's if and only if the code at my the second step is optimal, which is optimal if and only if my code at the third step is optimal. And at the very end, you're just left with 2 nodes because the last 2 nodes are just 0 and 1. So that is definitely optimal, right? So it's that sort of inductive proof where every step you show that this step is optimal. And at the end, you get to the base case, which is optimal. Will not do it. You don't need it for the homeworks. It's interesting. Read about it. Greedy algorithms you will often see like the proofs are sometimes a bit tricky. So this is one of them where like you need some amount of like math writing to prove it, but fundamentally this is the idea. So the first thing, as you might have observed, it's a greedy algorithm, right? We don't try to like do some sort of global optimization. At every step, we just take the 2 smallest things, merge, 2 smallest things, merge, so on. So that's something. Works for general Wi is greater than equal to 0 to solve this sort of problem. Like if you have any weighted optimization problem, right, they need not be probabilities is what I'm saying. You can take any W's and it's the same algorithm, it doesn't matter. So sometimes you will see applications of Huffman codes beyond just coding in some other areas. You might see some of them in either this or the next homework. And one last point is, this will be very important for this homework, so just be very careful. The tie breaking, right? We said that like if you have 2 possibilities, then like if you have 3 nodes, each of them have 0.2, 0.2, 0.2. You can either merge the first 2 or the second 2 or the first and the third. So there is a non-determinism sort of built in. The construction is not deterministic. In many cases, you can have more than one possible optimal Huffman code. So when you do the homework problem 5, be very careful. Last year, lots of students have a lot of issues. So just be careful that the tie breaking step in particular means that you have multiple possible Huffman codes, right? All of them will have the same expected code length. All of them are optimal, but they are different. Okay, last thing, let me go back actually here. No. Okay. Last thing is that for Shannon codes, we saw that expected code length is between hx and hx plus 1. For Huffman codes, that's basically what we have. We know, maybe let me write it like this. So we know that hx greater than equal to expected length of Huffman codes, which is less than or equal to expected length of Shannon codes, which is less than hx plus 1, right? So this is sort of the chain of inequalities. So Huffman codes are somewhere between Shannon codes and entropy. For certain types of distributions, you can prove stronger results, but really this is what you have. Okay, coming back to the construction. Can somebody suggest how do I do this step? How do I always pick the 2 nodes with the least probability? Can I do it in an efficient way? Maybe even in inefficient way. Just any ideas on how we can pick the 2 nodes with the least probability? How would you do it if you were implementing it in Python, let's say? Yeah, correctly suggests that you could use a heap or a priority queue, which is a data structure where you can always pull out the lowest thing or the highest thing depending on the type of heap or priority queue you're using. If you're not seeing those, it's fine. Just you should be aware. There is an inefficient way, right? You take the list of nodes, you sort it. You take the 2 lowest ones. Then you add the new node, the N1 node, and then you again sort it, and then you again take the 2 lowest. That also works. It's less efficient, but it works. Heaps or priority queues are, I guess, easier. Another thing to note is that in many situations, you will construct the Huffman code once and use it multiple times. So it's fine if the construction is a bit slow, because ultimately, like, you're going to construct it once for a distribution and then keep using it for lots of symbols. Okay, let's actually look at a code for constructing this in the library. Let me know if I need to zoom at some point. So we go to SCL, we go to compressors, we go to Huffman coder. Okay. Right. I'll sort of walk you through it. The file is this one, Stanford compression library, SCL compressors, Huffman coder.py. Right. So that's the file if you want to later look. So what we do is we define this thing called a Huffman node, where the Huffman node has a less than equal to implementation, which just says self.prob less than equal to other.prob. So basically what we are saying is you are creating this class in Python, which has this ordering property that you can define which node is bigger than the other node based on their probabilities. Okay. So then there is a function called build Huffman tree, which is what we were just doing. So let's see what the function does. If the length of the alphabet is 1, right? So if you're at the last node or there is just one node, there's nothing to do. You just, that's sort of the base case, I guess, of the recursion. What else? You start with a node list equal to the empty list. So I'm here. Yeah, okay. Then you, for A in self.alphabet, you create these nodes and you append them to the node list. And then you use this function called heapify, which converts this thing into a heap. Right. And then you have a loop where while the number of nodes in your heap is more than 1, you first heapify the thing. Then you take the 2 smallest symbols, right? Very easy. You pop from the heap. And then you create this combined symbol, which we were just talking about, right? So the last 1.prob and last 2.prob. You create a combined node and you push it back into the heap. And at the end, you're left with a single node, which is the root node of the thing. Right. So basically the construction we saw, you can very easily code it up in like less than, if you remove the comments, it's like less than 10-15 lines of Python really. So very simple. And any questions on this? Okay. Yeah. So depending on whether you like find you learn easily with code or with like this sort of pseudo code, you have both options available. So one topic which again connects to the homework question 4 is decoding. So if you remember, we in lecture 2 actually we talked about like you have these prefix codes, they can be represented with trees, so the decoding is so easy, right? You just walk down the tree, you decode a symbol. We were very happy, right? So we talked about this tree-based decoding, right, where the idea was very simple really. You have this tree like this, 0, 1, 1, 0. And then you had like a stream which was like 0, 1, 0, 1, 1 sort of thing. And then you would like go here, then you would go like this, and then you would go like this, and then you would decode it, right? Yeah, sadly, like nobody uses this. This is not a good idea in practice. 2 reasons. One is there are too many branches. Branches in the sense that if you write the Python code for this, there is like if-else statements. Like if this is 1, go left. If this is 0, go right. That sort of branches, right? So like this sort of thing. If 0, left. If 1, right. And branches are really, really bad for modern computers. So modern like computer architectures. We won't do a computer architecture course right now, but in short, the reason is they do something called pipelining, where they sort of collect a bunch of instructions and try to execute them in a pipelined way. And if you take the wrong branch, then you have to flush the whole pipeline. A lot of work goes to waste. So it's just bad. Like branches are bad. Even though you have good branch predictors, still branches make your code really slow. And you might wonder, like, why do we care, right? Do we really like decode so much data with Huffman? Actually, we do. Like gzip, one of the most popular compression formats, uses Huffman as its entropy coder. And every time you download a file from the internet, there is probably a Huffman coder running. The older video codecs used to use Huffman. Newer ones, I don't know. Every time you're streaming a video over YouTube, either this or something similar is actually running. You're always decoding a prefix code. Like anytime your computer is running, you're probably decoding a prefix code somewhere. So this is not just about Huffman, right? This is about any just this tree-based decoding is a really, really bad idea. Because of these branches, you will never get the same sort of video throughput that you get today. So let's look at an alternate way. We'll look at it briefly now, and then later in the homework, you will actually implement the decoding. This is question 4 of the homework. Oh yeah, you implement it in the context of Shannon codes, but the idea is like the same. So I will briefly describe it so that you have some context when you start the homework question. So there is a decoder state table, which is like 0, 0, 0. Actually, let me draw code here. So we draw this code. A is 0, B is 1, 0, C is 1, 1, 0, D is 1, 1, 1. Okay. So this is decode state table. And then you have another table which is called encode len, which is A, B, C, D, 1, 2, 3, 3. Anybody wants to guess what the decode state table is doing? This is all corresponding to the code I made on the right, the A0B10, that one.
You can basically just grab 3 bits at a time from a sequence and then check, which symbol it corresponds to in the decode state table. And then from there we can advance forward based on encode length, since not all of our symbols are 3 wide.
Yeah, so this was basically the full answer. So let's start step by step, right? So what does it mean that, what does it mean that 011 is decoded to A? What does that mean? Why are there like 4 things? 000 is decoded to A, 001 decoded to A, 010011. Why are all 4 decoded to A? Just try to guess. I haven't obviously told you what we are doing. But if you had to guess.
So if 256 is A, like 0, can only be encoded to A.
Yeah, so the answer is you look at the prefix, right? Like just the way we were doing the prefix coding, prefix decoding in the past. You look at a sequence, right? And you try to find like the first symbol that you decode out of it. So if you see a 000, the first symbol you would decode out of it is a A. It starts with 0, that's the only code word that starts with 0. If you see a 100, if you see a 100 or a 101, the first symbol you would decode is a B, because the B is the only one that starts with 10. Right? If you see a 110, then you would decode a C. If you see a 111, you would decode a D. So, with sort of this in mind, you can like define, you can implement this sort of function. I think this is actually not what you are asked to do in the homework. You are asked to construct these state tables in the homework. So, I'm not infringing upon your homework here. So this is, we call it decode symbol fast in the sense that it's faster than doing it in a tree. So you define this state, which is you take the 3 bits from the bit array, the next 3 bits from the bit array, you look at the decode state table, and you can decode a symbol already. Like you can decode that based on the 3 bits, you can decode the symbol. And then you look at the encode len table, which tells you the length of the encoding. And then you can like basically return S and the number of bits. So it's like a few steps of things to do. First thing is you take the 3 bits, next 3 bits from the bit array. Based on those 3 bits, you decode one symbol, only one symbol. So you can decode any of these ABCD symbols. Then based on the symbol you decode, you check how many bits do I actually need, like how many bits I have actually read. And then you basically advance. So that's sort of the process. And you will get much more practice with this in the homework, but here I just wanted to give you a flavor. Any questions on this? And if there are no questions, can somebody tell me what this 3 is? Why 3? What's so special about 3? Yeah, I hear that 3 is the longest code word here, right? Yeah.
I have a just question.
Yep.
What situation would we have this bit array with symbols of 3 when we're dealing with the prefix code? Like it just seems.
Yeah. So the way to think about it is that you are given a long sequence, right? Like it's just a stream sort of coming in or a big block or something, right? You have encoded like a bunch of ABCDs together. You got like a long bit array. And then you take the first 3 bits. Based on that, you decode one symbol. And you know that you have read maybe 1 bit. Maybe it was an A, so you only read 1 bit. So next time you will look at, so if the first time you look at bit 1, 2, 3, next time you look at bit 2, 3, 4. And then maybe you read 2 symbols. So now you have consumed bits 2 and bits 3. So now you look at 4, 5, 6. So that's sort of the progression.
It just
Yeah. I think we talked about it a little bit earlier. I think as you do the homework, you will get more experience. But see, the whole reason why we talk about all these prefix-free codes, why do we need prefix-free codes? Why is it not sufficient that A, B, C, D just have different code words? Why the prefix-free property? It's because almost all the time you don't want to encode just one symbol. You want to encode a long string of symbols. So the thing you encode is like A, C, D, B, B, D, D something. And that whole big thing will be converted to a long bit array. So like 0, 0, 1, 1, 0, 1, 0, whatever, right? So you get this long thing. And then that long thing you should be able to decode back to the original sequence. Look at the lecture 2 slides where we talked about, like there is an alternate approach like in a Morse code or something where you put a comma or a separator between every symbol. But that's not how we do it typically. It's not optimal. So it's better to do like have it prefix free so that you can encode a long sequence into a long bit array. So that's how you get the 3 basically. At the very end, right, like you might reach the very end of the thing where maybe you don't have, like it's not a multiple of 3 or like there is some boundary conditions. So you can sort of pad it with zeros just to make sure it works out.
I wanted to just clarify the last point that sure, like there may be some edge cases, boundary conditions. So suppose you are encoding AB 010. In that case, you read 3, you decode it, say you can only decode one symbol. You are still left with 10. But that's just a corner case. You can just always append last bit as 0 if it's not a multiple of 3. Read 100 and that's B again. That's where you stop the decoding.
Yeah. So Pulkit is talking about padding basically that at the end you might not be left with 3 symbols when you decode a long sequence. You just pad it with zeros. It's fine. Okay. Any other questions? Sorry. So one more thing about a couple more things about table-based decoding. So the size of the table is exponential in the maximum depth of the tree, right? We saw that in the last one the table size was 8 because 2 power 3 is 8. And what you want is, like in practice, you want it to fit in your cache. So it should be very small so that your decoding can work very fast. So therefore, you want to limit max depth. So this is something we will not do in class. Last year, a couple students did it actually as a project, but there is something called a constrained Huffman code, where the idea is best code with max depth constraint. The construction is slightly more complicated than your usual Huffman codes, but these are the version of Huffman codes that you will often see being used in practice. You want to constrain the max length, and often you want to constrain it to like 16 or 24 or like a byte multiple thing, so that it works nicely with like how computers work. Any questions on this? Yeah. So this is like really low level stuff, but you will see a lot of action in compression is often in the very low level stuff. You have a good algorithm, that's good, right? But if it uses all these complicated trees and so on, you can't use it for the large volumes of data. Videos are huge, logs are huge, text is not that big. So if you're just compressing text, go all in. But like for practical types of data, it's often like so big that you can't afford like suboptimal types of things. Last thing, just on table-based coding, the last thing, table-based decoding. More of a homework, really. Does anybody recognize this sequence? yeah, some people are correctly answering it's the Fibonacci sequence, right? What is the sum? So 1 plus 1, 2, 2 plus 2, 3, 4, 4 plus 3, 7, 12, 20, 33, right? So we make this probability distribution. Make this probability distribution. Just make the Huffman code for this at home. What you will observe is that this is like an adversarial case where you will get really, really long code words, right? Like you might think that why worry about this max depth? In practice, you will never have a very long code word. All the code words will be short and so on. But there are these special distributions where you will see that the max depth in this case will be basically equal to the number of symbols, or that minus 1, something like that. So the max depth will be roughly equal to the number of symbols. So you will get a really, really long code word like 1, 1, 1, 1, 1, 1, 1, 1, 1, so on. So solve it at home. Hopefully you enjoy it. Okay. Moving on to some practical Huffman codes. So first thing, this is like somebody did a nice experiment where they took a keyboard and the height of the letters on the keyboard are the frequency of that symbol. So E is like very, very high, T is the second highest, A is the third highest, right? So just in English. And then they also made this Huffman code for this distribution. And you can see at the top part, for example, that, sorry. Okay. Yeah, so E you see, E is like very short code word. Z, Q, X, J, like the less commonly used letters in English, are much longer, right? But it's non-trivial, right? If you didn't know the algorithm, like this is the optimal code for this distribution. So just something. At home I did a few more using SCL. So I followed basically Pulkit's tutorial of SCL. I installed SCL. I downloaded this very famous book, which I guess you know, Huckleberry Finn by Mark Twain. Right? Oh yeah, let me make it a bit bigger. Yeah. Right. So it's an English book, right? Normal English text about treasures and so on. And then I used SCL to create the Huffman tree for this distribution. We will post this and take a look, but you see like the letter small e is like very short code word. Letter capital E, the uppercase E is like much less common, right? Because E is very common, but E doesn't often come at the start of a word, of a sentence actually, right? Okay, we'll try to scroll down. Then what I did was I actually used sorry, this is just hard to do now. Is it visible? No. Okay, yeah. So I actually compressed it with the Huffman code. So I started with a 622 kilobyte file, 622542. It got compressed to 348142. So nice. With Huffman codes now you like can compress this one book to about like you can reduce it by 44%. So that's good. Okay. Then I thought like maybe let's compress another file. So I took this Apache Camel, which is a Java library, and which looks something like this, like you have these function calls and semicolons and symbols that don't occur as commonly in English, but they occur more commonly in code. And when we get there, we'll see. Okay. So one thing you see here is that, see this parenthesis, right? These parentheses get a much shorter code word than they would have gotten in normal English, because a code has many more parentheses than like English. And similarly, semicolon is like much shorter code word. The semicolon you see right below the parenthesis. So depending on your data distribution, your Huffman code will look very, very different, right? And that's the beauty of it. Like any distribution, you create the optimal code for that distribution and then use that one. Okay. Last one. Okay, here also I tried to compress it. This one compressed by about 40%. The last thing I did was I took an encrypted file. So the encrypted file was not, it's bytes, right? It's not like human readable English. So I made the Huffman code on the bytes. Look at this Huffman code. Anybody tell me what do you see in this Huffman code? Yeah, you see that all of the symbols have same depth, right? They seem to have all the same depth. Can anybody explain why the encrypted file gives me this strange looking Huffman code? Why did all code words get the same length? This is basically the fixed length code that we saw in the first lecture.
If it's not like this, then you can basically map it back to English word frequency.
Yeah. So typically, like most encryption algorithms, what you will see that their output is IID uniform sort of, so it's uniformly spread across the bytes. And the reason is something like it should not leak any information about the original distribution. So that's why all inputs go to the uniform distribution for a good encryption algorithm. Here I think we used AES, which is like one of the state-of-the-art encryption algorithms. See, you see all of these, the whole tree, everything is of the same length. So just use, so one lesson here is that like you can't compress encrypted data, right? You have like this, there is just some fundamental incompatibility. Like after encryption, if you want to compress something, do it before encryption, not after encryption. Because encryption will basically destroy all structure in your data. The data will look completely random to any compressor. It will not get any compression at all. So if somebody comes to you, right, with a startup idea, I can compress every file you give me by 50%, give them a encrypted file, see what they do. And I guess if they're able to compress that encrypted file, that means they have like broken AES. So that's a good thing. Most likely they won't. Okay. Is that clear? That the encrypted data is random. It's like IID uniform. It's not exactly IID, but it's close to IID uniform over all the bytes. So 0 to 256. So you will spend basically 8 bits per symbol there because each of the byte is equally likely. Okay. Right. And then I actually ran the compression right here. I think you can sort of see. Let me try to zoom in. Basically, you get compression rate of 1, which means that there is no compression at all for the encrypted file. So this is a we'll post the slides. Okay, so there are a couple more things about Huffman codes that we will not try to cover today. We will wrap them up in the next lecture. But after we cover those very small topics, the next lecture will mostly be about theoretical intuition behind entropy and block coding. Why entropy? What's the importance of entropy? Why does block coding works? How does it interact with like large laws of large numbers, probability, and so on? So Professor Tsachy Weissman will be taking that lecture. And next week, we'll start talking about practical block codes or stream codes, which actually get very close to entropy. And they are the ones that are used like for the state-of-the-art, basically, compressors. So with that, thank you. Let me know if you have any questions.